Hello, my name is Faris Khundakjie. I'm a senior technical lead at Intel and the chair of Accellera Portable Stimulus Workgroup. Thank you for joining us to learn about this new and exciting standard under development. We believe this standard will enable the next leap in verification and validation productivity and quality. Essentially, with this standard, the verification and validation community will be able to express test intent once, then use verification, validation tools and technologies that process that intent into tests and implementations that run across multiple execution platforms, such as simulation, emulation, virtual platforms, and post-silicon, across different levels of integrations, from IP to SoC, with and without software and firmware, under different configurations, and across multiple user roles and responsibilities. In this section, I will explain the motivation for portable stimulus, what portable stimulus is and is not. I will go over a few problem areas that explain how portable stimulus might be able to help. I will give an overview of the standard need and the standard direction. I would like to thank my colleague, David Brownell from Analog Devices, for his invaluable contributions to this section. I would also like to thank all of the speakers and presenters for the upcoming sections that will take us through the next level of detail, from Mentor Graphics, Cadence, Breker, Synopsys, and Viavia. Please sit tight and enjoy the ride. Let's first start by acknowledging the tremendous evolution in verification over the past 20 years or so. From the days where verification was at its infancy, where the research and development effort was dominated by design and architectural innovations, along with manual labor of design synthesis and layout, to the introduction of directed testing, to witnessing design versus verification camps and separation of responsibilities due to increasing product complexity and increasing knowledge in each of the domains, to the introduction of verification languages such as System Verilog and verification techniques such as constraint random verification and model-driven verification, and to standard verification methodologies such as UVM, VMM, and OVM. It is possible to have a similar description of the evolution in system validation, in particular post-silicon validation, to show the evolution from pure diagnostic activities to directed testing, to random testing, heavy concurrent testing, and synthetic testing, as well as testing with system production software and firmware with operating systems. And what we've been witnessing over the past several years is our inability to grow with this current approach or these current tools to the next level of productivity. We think we need this next level of productivity to address the increasing complexity of system-on-chip integration, the sophistication that needs to go into IPs that plug into different and many market segments, and to have a path to share and communicate and overlap our activities for increased productivity and shortened product lifecycle with other platforms and the engineers and their activities in these other platforms. We think portable stimulus can be the bridge to that next level of productivity, and we hope to show that in this section. We expect portable stimulus to have an impact on several areas. However, these areas are the key ones where we see the largest productivity and quality gains. It is obvious that portable stimulus will reduce the effort in writing tests, because by definition, portable stimulus is expressing a verification intent once. Unfortunately, today, we still see replication of use cases written using different stimulus languages and different technologies on different execution platforms. And while we have today a single specification for a product, we may not necessarily have a single interpretation of that specification due to disjoint activities in different platforms and even sometimes in the same platform. Over the years, we have grown expert knowledge in utilizing every single one of the platforms using its distinct advantages. However, we have not really mastered the utilization of the platforms combined to reduce the overall investment in the product and in shortening the product lifecycle. We expect portable stimulus to drive a consistent and efficient utilization of all the platforms combined. One key product of test plans or verification plans is producing stimulus. By having portable stimulus, we are encouraging and effectively enabling test plans to be a continuum across multiple platforms. It is also not sufficient to have just the description of test plans or verification plans be portable or be relevant to multiple platforms. The execution and the verification and validation knowledge that has been acquired throughout the years needs to be captured and reused across platforms where necessary. Rather than continuing with current development practices where the top activities and roles are done with assumptions on the execution platforms or at least sensitive to the execution platforms, these activities would be refactored or detailed to include portable stimulus development activities such as expressing models and use cases or scenarios and generating artifacts such as prototype device drivers that can run on 2 or more execution platforms. Before going further, let's first clarify what portable stimulus is and is not. Again, portable stimulus is a single representation of test intent. By that, we mean a collection of constructs such as types, classes, and expressions, and the rules governing these constructs and expressions that will be all reusable by a variety of users across different levels of integrations in a variety of execution platforms and under different configurations within the same platform and across multiple platforms. Portable stimulus should not be misunderstood as a way to force everyone to think at a certain level of abstraction. We acknowledge, for example, that design verification will continue to focus on transactional testing and pipeline designs, and verification engineers in that space are still focused on that level of control. At the same time, we acknowledge, for example, that system validation or virtual platforms will focus on software readiness for the product and the interactions between the software and the hardware or firmware. It's also important to realize that portable stimulus is not a monolithic piece of code. It is not the expectation that one source or one vendor for portable stimulus will provide all that is needed. The intent is to create an ecosystem of multiple libraries coming from different sources, all written using portable stimulus, and all could possibly interact to build in a modular fashion a much larger model and set of scenarios. And finally, portable stimulus is not intended to replace all activities in a single platform. We acknowledge that certain standards will remain common and will be continuing to be the right choice for specific tasks in specific platforms. Some of you may be familiar with the standard for verification methodology in simulation called Universal Verification Methodology, UVM. You might be asking yourselves, why is UVM not good enough? What does portable stimulus solve that UVM does not, and why should I use portable stimulus? It's important to recognize the tremendous value that UVM brought to design verification. After years of evolution of verification methodologies, we finally have a converged common language and framework for verification engineers to execute and communicate through. In addition, UVM has a modular and smart test bench architecture that allows reuse for passive components such as monitors and checkers. However, for engineers that are closer to system-on-chip verification and validation, and those outside the simulation environment, System Verilog and UVM continues to look like an overly complicated and hard-to-debug environment with many layers. The simplest of tasks, such as creating a directed test, seems to need a high barrier to entry in UVM. So while UVM is excellent for block and IP level verification, and especially for promoting reuse of passive components, its continued path of building on its predecessor verification methodologies in terms of implementing stimulus as transactional stimulus using sequences that communicate with drivers and BFMs, inhibits its abilities to make such stimulus portable to system level. For example, how would one translate a UVM transaction to a C or an assembly instruction in an instruction set that lives in a code image, loaded in memory and fetched automatically by a core or a microcontroller? It's also not fair to expect UVM to cover the needs of other platforms and the roles of engineers in these other platforms, from software enabling to post-silicon or evaluation and fast speeds were never part of the UVM scope. If we were to reinspect the common product development cycle today, we would notice multiple roles, multiple focus areas, multiple platforms, and many development languages. We could possibly focus on specific inefficiencies in the current development cycle. We could look at hard boundaries across the different roles, or across multiple roles and focus areas, or across platforms and the inability to share languages across different platforms or the need to use specific languages for specific platforms. When in reality, what we really need to do is to revolutionize this development cycle using portable stimulus and bring down as many of these boundaries as possible. Let's take a look at examples of potential capabilities and benefits of portable stimulus. In the area of stimulus reuse, expect to see IP functionality and features divided up into sets, and subsets of these will be made reusable using portable stimulus at subsystem and SoC. Not only that, take multiple use cases from multiple IPs and run them in parallel or in isolation, horizontally across multiple platforms, simulation, emulation, and silicon. Portable stimulus will also enable the reuse of failure cases from evaluation or silicon boards to the IP test environment. As part of portable stimulus standard, we're also focused on simplified test authoring. Portable stimulus will drive the verification stimulus library ecosystem. It will make coverage-based test creation mainstream. It will allow us to crisply define data flow from one IP part to another and from one IP to another in the system. And in the area of improved collaboration, expect test visualization to help us conduct better reviews and have better communication. Expect improved debug efficiency. And when it comes to future technologies, as you will see in follow-on sections, the nature of the portable stimulus standard being developed is lending itself to formal analysis and future machine learning techniques. We would like to emphasize that the portable stimulus standard under development is not limited to making stimulus reusable. There is added focus in this standard around added levels of test generation automation and simplified test authoring. Both of these will lead to increased adoption of the standard and increased productivity, as well as increased quality of verification and validation. We need to recognize that the customers of this standard have different roles and different perspectives on what a test means to them. For example, architects may focus on throughput, latency, and quality of service. Block or IP design verification may focus on microarchitectural aspects, functionality, and performance at that level. System design verification may focus on correct connectivity, use cases at the system level, and system robustness. We recognize that existing languages are not natural nor expressive enough to cover all these points of view and to offer a simplified test authoring input. An architect would want to write tests from a system point of view, to see multiple DMAs, for example, running in parallel. IP or block level verification may want to focus on exercising all the modes, all the error conditions in random combinations that may or may not be realized at the system level. System design verification may focus on fabric connectivity to the IP block, or write tests to ensure that all memory regions are reachable or accessible. Now let's walk through 3 examples that demonstrate how portable stimulus may interact with your target execution environment at a high level. Take the case of transactional reuse. An IP use case may be made up of a flow of register writes and pulls expressed in portable stimulus. A portable stimulus tool reads that use case and generates UVM RAL sequences that communicate to a UVM target driver in the IP simulation environment. It's possible that these UVM RAL sequences are either existing sequences in your environment that just needs to be communicated to, or that a portable stimulus tool might generate these sequences for you. Take the same IP use case written in portable stimulus and generate a test case in an SoC simulation environment where the driver is not present from UVM, and instead at that boundary we have a real core instantiation. In this case, a portable stimulus tool would generate a C-test of memory mapped register accesses. However, for a large SoC, not all cores may be instantiated, and some instances may still have a driver in UVM. It's expected that a portable stimulus tool will continue to generate or communicate to UVM RAL sequences in these instances. It is also expected that such a tool may synchronize the execution of both register accesses or these register accesses on different instances. Another example is the reuse of a software driver prototype. In an IP simulation environment, we may have a software driver prototype that's expressed in portable stimulus, mapped to a short UVM RAL sequence or set of sequences. When we try to generate from the same software driver prototype in SoC system level emulation, a portable stimulus tool might extend the length of the generated code and might make it in C, so it would be a medium length driver prototype generated in C. And when we go to a silicon board or a post-silicon tester, that same software driver prototype would be translated by a portable stimulus tool into a large length driver prototype in C. That's because we can afford to have large test cases or much larger test cases running in that platform. Another case of unique interaction with the target environment is software and firmware awareness. Take a simple abstract memory allocation in portable stimulus. A portable stimulus tool may simply delegate to a C library with a linker managed memory in an SoC system level emulation environment that's running a Linux operating system. So the linker is doing the work of managing the memory allocations. In the same environment, where there is no operating system and there is no linker, sometimes called bare metal, a portable stimulus tool may generate code in C that interacts with a custom memory manager, similar to those that you might be writing in your own C tools or in your UVM environment. It's important to note here that our references to PSS tool do not indicate anything that is part of the standard. Only the top layer in these examples of specifying models and defining scenarios and use cases is what is expressed by the portable stimulus standard. With portable stimulus motivation, potential benefits, and deployment examples behind us, let's now discuss why we think there is a need for a portable stimulus standard. UVM has really enabled the growth of a verification IP ecosystem. With portable stimulus, we expect that growth to now go beyond verification ecosystem to include verification stimulus libraries and validation across multiple platforms. We expect this to accelerate even further with EDA-provided portable stimulus libraries. Another possible benefit for a standard is to empower standards bodies, such as PCIe SIG, to produce compliance test suites that use portable stimulus. Having a standard can focus EDA vendors on the next set of challenges, and having a quick and mature answer for common and known challenges today. Of course, the real benefit of the standard is to increase predictability for the mobility across platforms and vendors for user companies. For example, your emulation and simulation EDA suppliers may be different. This is enabled by the fact that the standard has the same input regardless of the platform, and the standard dictates consistent semantics for that user input and experience across the execution platforms. We would like to point out, though, a unique aspect about this portable stimulus standard. There is no reference implementation provided. So unlike some Accellera standards like UVM and System C, Portable Stimulus Standard will not include any reference implementation. This is simply because we have a large number of possible implementations from many vendors, and a large number of techniques to approach solving very different problems across platforms. The second fundamental reason is we would like to leave room to foster innovation across vendors and technologies as the applications of portable stimulus mature. The specification and its supporting material do not describe how any vendor implementation works. Vendor implementation is really responsible for processing user input and generating and executing tests that interact with user execution environments. If you have any questions on a particular vendor implementation, we call this secret sauce or PSS tool. These questions should be discussed directly between users and vendors. However, we make best effort in the examples we provide to help the user community visualize possibilities or modes of interactions with the execution environments. Portable Stimulus Standard defines new fundamental semantics. At this point in time, we are not aware of any existing common language, general purpose or other, with its specifications and associated compilers that can satisfy all current and future portable stimulus semantics. This includes, for example, scheduling rules and resource assignments. For example, the System Verilog IEEE standard defines scheduling regions. This definition was created and optimized with simulators in mind. So, while it might seem that syntax from System Verilog might be appropriate in some cases for portable stimulus, the underlying scheduling semantics are not. Another example is the reuse of C++ and C++ compilers as is. It might not be obvious that loops and memory allocations have to be translated by a portable stimulus tool to unrolled versions or different mappings depending on the target platform. In this case, these kinds of actions cannot be fully delegated to a C++ compiler off the shelf. So in order to balance the need for having an input optimized for expressing portable stimulus and the situation that users across multiple platforms are familiar already with some existing popular languages, the Portable Stimulus Standard defines a new domain-specific language that offers a natural and concise way for users to define portable stimulus input. At the same time, to ease the adoption into multiple other platforms outside simulation, another input based on C++ is defined by the standard. This input will have matching semantics to the domain-specific language. This is critical, and semantics refer to the meaning of things. The C++ input will also be consumed or is expected to be consumed by a portable stimulus tool. Compliance with the standard will imply at least the ability to process one of these inputs. This concludes the end of the first section. We hope by now that you understand the need for portable stimulus and a portable stimulus standard. Please stay tuned for follow-on sections that have a wealth of material and detail on the standard.
Hi, I'm Tom Fitzpatrick of Mentor Graphics and the Vice Chair of the Portable Stimulus Working Group in Accellera. This section of our tutorial will explain some of the key concepts and constructs in the new Portable Stimulus Standard. We've always relied on raising the abstraction level to improve verification productivity. When design moved from the gate level to RTL due to synthesis, we were able to only randomize numbers as part of our verification using $urandom and other similar functions. UVM allowed us to move our verification from the RTL to the transaction level and introduced the idea of constrained randomization of transactions using the randomize method. It also allowed us to randomize the structure of the test bench and do some additional customization using the build method and the config database. With portable stimulus, as you'll see, we're moving from the transaction level up to the scenario level. So portable stimulus lets us declaratively specify the key intent of the stuff that we want to verify. And then it allows us to randomize scenarios based on system level constraints for our target platform to allow us to realize that key intent that we specified originally. So let's look at what we mean. At the transaction level, in UVM, we would have a sequence that might generate a series of transactions. And suppose that transaction had 2 data fields that each had 3 values. So it would take us 9 loops through that sequence without repeating any to hit all possible transactions. At the scenario level, we want to think more about the operations that need to occur in order to verify the design. So we may have a compression decompression engine, so we want to be able to verify the compression action. And perhaps the system allows us to do a copy from a modem that receives the data and send that to the compression engine. The system may also support DMA to transfer directly from a UART that receives data into the compression engine. And it also may allow us to DMA from the modem as well. So with this kind of a setup, we may decide that we want to just verify that we can do the copy operation into the compression action. And then from just specifying that part, which is the key intent of what we want to verify, we can infer that we have to actually execute the modem receive action because that's the only way to get data into the system to then be copied to the compression action. Similarly, if we decide we only want to verify the DMA transfer capability into the compression action, then we may actually either do a UART receive or a modem receive action. So when we randomize this scenario, we will pick one of those 2 actions to support the critical intent that we specified originally, which is the DMA transfer to the compression action. So we use actions in portable stimulus to capture behaviors. So we have simple actions that map directly to target implementations, whether it's a UVM sequence or C code or whatever, as we'll see. And we have compound actions that we model via what we call activity graphs. So actions, as you'll see, are modular. They are reusable. They interact with other actions, and they have inputs and outputs to define the data flow requirements for communicating with other actions. They also claim system resources, and those are subject to constraints based on the target that you're actually going to be verifying. So there may be a target that only supports 1 DMA at a time, in which case you can only do that, or you may actually have multiple DMA channels, in which case you can do multiple actions in parallel. And as I said before, each of those simple actions will map directly to some implementation, whether it's C code or UVM sequence or what have you. And the activity graph defines the scheduling of the critical actions. So as you can see here, we can define scheduling constraints between the individual actions in our graph. And then we also use the data flow objects and the resource constraints to further refine the scenarios so that we make sure that we only generate legal scenarios to support the critical verification intent that we specify as part of our portable stimulus. So let's look at a simple example here. We have a UART that receives and transmits data packets via some data port in our system. And the system also supports doing DMA transfers of those data packets to and from memory. And these DMA transfers will be concurrent with the receive and transmit operations in the UART because the UART has no internal storage. And then there's also a command port that allows us to access registers and memory to do things like configuring the UART or the DMA transfers, and also to read and write memory data. And so we have specific data flow objects that allow us to describe these behaviors. So we have what we call a stream, which is an indication that there's no specific storage. So the producer and the consumer need to run in parallel. And we also have a buffer that actually represents storage. So the producer can produce the buffer, and then the consumer can consume it sometime later. You'll notice that both of these have a single component in them called size. These are 2 different data types, but they can be derived from the same basic data layout, as we'll see. So when we look at what the action might look like, we can have a read-in action for the UART that will take data in and actually will produce an output of this data stream type from the UART. And then there will be an action to transfer that memory through DMA from what we call Q, or the Q and the UART, to the memory. And notice that the output of the read action is the same type as the input to the DMA transfer. So that allows us to take that DMA packet stream and put it into the memory. Similarly, going the other way, we have an action mem to Q transfer, which has an output of data stream type and allows us to write that data out. So the actions are modular. The behavioral descriptions can be reused. So the behaviors eventually get mapped to either a piece of VIP in your test bench, or they get embedded in the CPU and the target if you generate code from them. And as we'll see, there's a flexible mechanism to map to different targets. The actions encapsulate their own intrinsic properties and also rules for interaction with other actions. And the actions represent functionality. So the first step is to identify the target design behaviors that need to be exercised. Then we have to figure out what data do these behaviors either require or produce. Then we look at where the behaviors are executed. Are they executed in the DUT, or do they require VIP? And then we look at what system resources are required to accomplish these behaviors. And notice that these questions are independent of the implementation details of the DUT. We're only worried about what the DUT has to do. We're not worried about how it actually does it. So let's look at a basic scenario here. So we're going to look at the data receive action. So we declare that action. We use the keyword action. And then we can declare sub-actions inside of that. So in order to receive data, we have the read-in action and the Q to mem DMA transfer action. We can declare constraints, and these constraints can be named. They don't have to be, but they can be. So here we're going to say that the size of the packet being transferred is a word align. We can then bind the inputs and outputs of the sub-action. So we're going to say the data output of the read action is the source data for the DMA action. And then we use the activity keyword to define this graph of sub-actions that we're going to create. So in this case, we're going to execute the read in and the Q to mem actions in parallel. So both of those two actions have the same predecessor. In this case, it's just the beginning of the graph. Notice the output of the read is the input to the Q to mem. And we also have, as was mentioned, the option of specifying the same functionality in C++ if that's a language that you're more familiar with. So notice we do the same thing. We declare the action. We have an action class. So that's in the library. So your action will get derived from that library class. And the activity is defined as a tree of library class instances that represent the statements. So the only thing that's really different here is that we have to register that type in the PSS library using the type_decal construct. This is different from decal type in C++11. So it's just a way of registering that type with the portable stimulus tool. So activities are kind of nodes in that activity graph. So they're sort of the action instance is a thing that's going to occur as part of the behavior that you specify in the activity. It optionally allows you to specify inline constraints. So here we can say we're going to do action A2, but the F field is going to be constrained to be less than 10. And a node may also represent a variable randomization. So we may have some variable I that we want to execute. And by default, activity statements execute sequentially. So that means that the final bit of activity n-1 completes before the initial thing inside of activity n starts. So for this particular activity that we've specified, A1 followed by randomizing I followed by A2, you can see what the timeline looks like. And we're just assuming that each of these actions will take some time in the target implementation. We don't care how much it is, but all we know is that these things have to execute sequentially. So activities allow you to specify some really robust scheduling. So there are parallel branches which start at the same time, which means that the initial actions in all of the branches have the same set of predecessors, and there can be no cross-branch dependencies. So we may have two instances of A that execute sequentially, And we may have two instances of B that execute sequentially, and those two sets of actions start at the same time because they have the same predecessor and there are no dependencies between them. We can also use the select statement to randomly choose one branch from the block. So in this particular example, we have an A followed by some ordering of B and C to allow us to meet whatever other scheduling dependencies are there. So we may do A followed by B, or we may do A followed by C. So we are going to do one and only one branch of the select statement, and that will follow A. So this is an example of randomizing at the scenario level. This one specification allows us to do either AB or AC. We also support if-else blocks, do-while loops, repeat, and for each element of an array. And then there's also a really useful thing called a schedule command, which allows the actions in the schedule block to execute in whatever order is legal given the constraints. And this is different from the select block in that all actions must execute. So in this case, we're going to do A followed by some combination of B and C, and it could be B followed by C, C followed by B, or B and C in parallel. Now, we mentioned flow objects before. These are what specify data flow, and they have some scheduling associated with them. So they're user-defined data types. You can kind of think of them as special types of structs. They can inherit from a struct type, but they can't inherit from each other. And they function kind of as action inputs or outputs. So we might have a struct called base S, and the buffer object defines sequential data or control flow. So you can think of them as either pre or post conditions for an action execution. These represent persistent storage, and after you write to them, they can be read any number of times. So we may have a start address and a mode. Notice the rand keyword here. So every time we create a new instance of the buffer, those fields are going to get random. The stream object is similar. It's also a type of struct, but this defines parallel data or control flow. So they model things like message or notification exchange, as we saw in the example, between the UART and the memory. So we had to execute those actions in parallel. We also have state objects that define the state of an element at a particular time. And writing to that state object, each write must be sequential. You can have multiple concurrent reads, but reads cannot be concurrent with writes. So you write once, and then you can read back, and then you can write again if you want. But you can only do one write at a time. And we'll cover that more in the next section. So for buffer objects, an action that inputs a buffer object has to be bound to an action that outputs a buffer object of the same type. So you can reference the outputting action either explicitly or, as we'll see, implicitly. Buffer object output can be connected to 0 or as many possible input actions, but they all must be of the same type. And in addition to being of the same type, the constraints must match as well, as we'll see. The producing action has to complete before execution of the consuming action may begin. So in this case, we have two actions, a consume memory and a produce memory action. And as you can see, the produce memory action has an output of data buff type, so that has to complete before the consume memory action can start. So notice we haven't specified an activity graph here for this. Just this information alone is enough to define the scheduling semantics between the producer and consumer actions. The stream object semantics are similar in that an action that inputs a stream object has to be bound to an action that outputs a stream object of the same type, and those actions can be referenced explicitly or implicitly. And an action that outputs a stream object has to be bound to an action that inputs a stream object of the same type. But the difference is that the execution of the outputting and inputting actions has to occur in parallel. So the only difference here from the previous example is we changed the buffer keyword to stream, so that now indicates that the two actions have to execute in parallel, as we see in the timing diagram. Since we're eventually going to be running these scenarios on a specific target, there may be constraints about that target that will force us to make certain allowances in our portable stimulus. So some of the actions that we specify may require resources on the target, whether it's DMA channels, a video pipeline, a compression decompression engine, a UART. So we use resources and we model these as user-defined types that are specialized struct types similar to the stream and buffer. And these are used to describe the information about those resources. And then actions may claim a resource for the duration of their execution. So locking an action excludes other actions from accessing the same resource. Sharing the action still lets you access the resource, but other actions can access the same resource at the same time. The test defines how many resources are available, and we use a thing we call a pool to define how many are available, and then those pools get bound to specific actions, so we say which actions can access the resources in a given pool. So here's an example. We have a resource called channel_s. We have a pool that has one element of it, which is the default. So there's one channel that's available. And we have two actions, transfer A and transfer B, that are each trying to lock that resource. And remember, there's only one of them. So that means that the X for A and X for B actions can operate in any order, but they can't overlap. So one has to complete before the other one starts. If we use the share resource option instead, X for A and X for C now, they're both sharing the channel resource so they can execute in parallel. They don't have to, but they can. And then if there's another X for B that's trying to lock the channel, that has to wait until both X for A and X for C have completed before it can start. So let's go back to the example and take a look at the resources. So now we might have a DMA channel resource, and there's an implicit attribute in the resource type called instance ID, which allows us to know which specific resource instance we're actually using. And we may also have a data struct that specifies the parameters for a DMA transfer. And notice all of these fields are randomized as well. So in our Q to mem transfer DMA action, we have an input that's a data stream type and an output that's a data buff type. It's going to lock the channel and it's going to randomize the DMA transfer parameters. And it also has constraints. So we have a constraint that says the size of the source and the destination have to be the same. And we're also going to constrain the parameters to something. So the source address of the DMA transfer has to be whatever the address of the source is, etc. So that's, we can put all of that information in the Q to mem transfer action. Or we can create a base action, we'll call base XFR, which defines the lock and the data transfer parameters. And then we can inherit from that to the Q to mem transfer, which will define the input and output, and also the constraints. And we put the input and output in the extension here because for the mem to Q transfer, as we saw, the input and output types are reversed. So in order to group things in a portable stimulus specification, we have this idea of a component. So the component is kind of like a type namespace. And we also have packages, as we can see. So we can import things from a DMA transfer package. And we use the same import syntax as System Verilog. And components are reusable groupings of actions. So you can define an action inside a component. Pools, which again define what the type of the resource is, how many of them there are, and what the binding is going to be. And also additional configuration parameters, if you'd like. So the pool is a collection of either object or resource instances, and the bind directive allows us to associate pools with actions and specify which actions can exchange flow objects of the given type and which actions contend for the same set of resources in a given pool. So in this particular component, we have the component called UART, and it has the read action and the write action, and it also has a resource of type UART. So you can only do one of these things at a time because there's only one UART, and each of the actions, read and write, tries to lock the UART in order to make that happen. In C++, it looks pretty much the same. So we have the public component base type, so our UART is an extension of public component. We have the read in and the write out actions, and notice the type decal specifications to register those. And we also have the idea of the resource and the pool and the bind. So everything we can do in the portable stimulus declarative language, we can also do in C++ in the declarative manner. So let's go back to our example. So we had the UART component that we just saw, and the DMA component is going to include the Q to mem transfer action, the mem to Q transfer action, and we may also have a mem to mem transfer action as well. So perhaps we can DMA from one area of memory to another. We have a pool of DMA channels, and remember by default there's only one of them. And we say we're going to bind that DMA channel to all of the instances inside of the DMA controller. So that's what the asterisk means. And similarly, in C++, we can do the same set of stuff. So we have the pool, the bind, and all of the class definitions. So our top level component, which in portable stimulus we always call PSS_top, will instantiate the UART and the DMA controller components. So we have a pool of data stream objects, and we have a pool of data buff objects. And these are used in the top level component to make them available to both of the components. So we can bind the data stream pool to anything, which allows us then to have the data go from the read in action in the UART to the Q to mem action in the DMA controller, and similarly the mem to Q to the write out actions. So the stream pool has to be in the top level component because it's being shared across the subcomponents, the DMA and the UART. Okay, similarly, the data buff pool is in the top level component, so it is available to all of the actions inside of the DMA component, each of which needs the channel resource as well. So we can use that data buff pool to transfer the data between each of the Q to mem, mem to Q, and mem to mem actions, and also to be able to transfer those out of the DMA controller to some other component that we might decide to use in the future. And again, we can do the same thing in C++. So in order to create a test, we use actions to specify behaviors that we want to accomplish in the design. So the actions define their inputs and outputs to communicate with other actions, and they claim resources that are target specific. Activities define the top level scenarios. So the compound actions define the high level intent of your verification, and the graphs define the scheduling of the actions in that activity. The resources and flow objects define additional scheduling constraints. So locking resources prevent other actions from using them in parallel. Stream objects require another action to execute in parallel. And buffer objects allow another action to execute sequentially. And the components group useful stuff to allow us to reuse things. So let's look at an actual test. Suppose we want to do a loopback test in our UART. So we want to receive data on the UART and DMA it into memory. Remember, these happen in parallel. We want to bind the output of the read action to the input to the Q to mem action. And then we want to DMA from the memory back to the UART and transmit it. And again, these happen in parallel as well. So the output of the mem to Q action is the input to the write out action. And then we have to bind the output of the Q to mem action to the mem to Q action. So the data that gets produced and stored in the memory as a buffer gets then DMA'd back out. Right? So we can explicitly set that. So this is a fully specified scenario here. This is the only thing that can happen. The read action will occur in parallel with the Q to mem action, produce a data buffer that will then get DMA'd from the mem to Q action all the way to the write out action. But we said earlier that we want to be able to randomize things at the test level. So the activity graph only needs to define the critical intent, right? The what we want to do. The flow objects and the resources constrain the possible scenarios, and a tool that supports the portable stimulus standard could infer supporting actions to decide how to actually accomplish that intent. So in this case, we only have to specify the read-in action, and we know that because it's producing a data stream, there has to be a Q2mem action to receive that data, and then that data has to get produced and sent to the mem2q action, which happens in parallel with the write-out action. So what do we do to make sure that the data just doesn't come in the read action and automatically get looped right back out to the write-out action? Well, remember we said that we have resources there. There's only one UART, and the UART cannot read and write at the same time. So we have the pool of UART resources there, and each of these actions is going to try to lock the resource so they cannot occur in parallel. So now all we really have to specify in the activity statement is we want to do a read followed by a write. And the read will produce a data stream object. So we have to have a Q2mem there, which will produce a memory buffer that the mem2q can use to create the data stream to send to the write-out action. Given all the information that we have, all we really need to specify is the write-out action, because it has to consume a data stream. So there has to be a mem2q action to produce that data stream, which means it needs a data buff. So there must be a Q2mem action that occurs before it to produce that data buffer. And the Q2mem needs a data stream input, so there has to be a read-in action in order to produce that. So we can infer those actions to create the legal scenario, given that the only thing we've actually specified is the write-out action. So it's subject to the constraints, such as the type of data flow objects that are flowing between actions, the resource constraints, and other scheduling constraints that we might put in the activity graph. So with the mem2mem action, it may be that we could also infer a mem2mem action in between the read and the write. So the Q2mem action produces a data buff that then gets transferred via the mem2mem action to create another data buff to do the mem2q to the write-out. So both of these scenarios are valid and satisfy the constraints that we've specified, given that what we really want to have happen is we want to be able to write data out. And if there were another way of producing data instead of the read-in, maybe using the control port to actually just fill up the data buffer, we could do that as well. And here's the same test specified in C++. So we have the two components, the pools, the binds, and the loopback test. And inside the loopback test, the only thing we're doing is the write-out. So the idea is that you use these constructs in the portable stimulus language to specify the key actions that you want to have happen and the schedule between them, and then the modeling constraints that you specify based on the type of data flow objects and the resources in the target and other things then allow you to infer from the critical actions that you put in your graph what other actions are necessary in order to make that a legal scenario.
Hi, my name is Sharon Rosenberg with Cadence Design Systems, and we're gonna talk right now how to achieve system-level scenarios with PSS. So before we start, let's talk about what are system-level scenarios and what are the specific challenges that we have with system-level scenarios. Well, we can definitely try IEPs in the context of a full system. That will be interesting. The main things we're looking for are things that are not there in the individual subsystem and individual IPs. So the whole is definitely greater than the sum of its parts, and so are the bugs. The logic that we're after is sometimes not there in specific IP and spread throughout the system. Here are a few examples. Application use cases that involve multiple IPs interoperating. Small example here. We can read a video of a mass storage device, decode it, split audio data from the video frames, and process by multiple dedicated multimedia engines. That will be a full use case scenario, systematic scenario that we want to try, and of course we cannot try with the individual subsystems. Stress and performance would be yet another thing. So we may want to put stress on an interconnect by throwing a lot of traffic from the subsystem at the same time. We have an example here. All processors and DMA-able controllers access a certain memory controller in parallel. What is that going to do to our system? Are the latency going to be correct? Is the system still going to perform with the use cases, with the intended use cases? System low power use cases. This is very key and important for many SoCs. So I may want to shut down several of these subsystems at the same time to achieve some system level low power state. And now let's see how things function. This logic may not exist with specific subsystems. Coherency would be yet another example. Think about cache coherency with the CPUs trying to write to the same regions and the same lines and try that systematic engine and logic. And of course, I/O devices trying to write, sometimes using SMMUs and shoot traffic at the same cache regions. All of these are very interesting for system level scenarios. So what we did to demonstrate PSS is we've created a simplified yet representative SoC example. And this is what you see here. So we have 4 cores in our CPU. Each one of them can do read, write, and copy of memory buffers. And we have a multi-channel DMA that we can use, a graphic subsystem that can decode images or video, a crypto engine that can encrypt information, and a UART device, the same UART device that you've seen in the previous section, and that can transmit and receive. So this is our simplified system here. And the process of going through it and modeling for PSS and creating the scenario is like this. Define the component types and their operations as actions. So DMA can do transfer, and graphic subsystem can do decode, and crypto can do encrypt or decrypt, and our CPUs that can do the write, copy, and read. All these operations are actions of specific components that we have here. Now I'm already in a state to automate the creation of a lot of scenarios. I can compose actions into activities, into full use cases. So I can ask all the CPUs to do write at the same time, and then do a loop of transfers, and then encrypt them and send them somewhere with my UART. That would be a system level scenario. So I can create these activities at this point, and they could be created hierarchically, right? I can call the scenarios that I've defined before and create a more abstract solution. And then I can instantiate the components, the amount of shared resources, etc. It seems a little bit awkward. Why am I doing it at the end? But this is exactly what we're trying to achieve here. Both the actions and the composed activity are not specific for a project or a project instantiation. And this is where the instantiation could come only at the end. I'm creating the scenarios in a way that they capture the pure intent, abstracting from the DOT configuration, the verification environments, the execution platforms. All of these are not needed on the phase of creating the activities.
You've seen this already, right? This is our UART. We have write out and we have read in actions to it. Here's a DMA. Just an example, right? We have a pool of resources, a memory to mem transfer. I'm reading, I'm writing back, I'm locking one channel. This constraint here that the size, because I'm just doing copy, the size here is equal to the size here. So that is what DMA. Here's the crypto engine, just another example. I can do encrypt. I read a memory buffer, I'm writing back a memory buffer, and I have some constraints that if I'm doing encrypt, my source is not encrypted, and my destination is encrypted. That's what encrypt is all about. So I just write it down, and maybe I have some constraint about the memory I can access. So I put them here, okay? Defining a very high level. Now I want to make a point about UVM. Let's go back to the UVM, which I think UVM is a great thing. Provided a lot of value to the industry from standardization point of view. But since the early days of UVM or UVM approaches, what do we draw? We draw that golden banana, right? We put the DUT, and then we model the entire environment surrounding that DUT, right? Oh, here's another interface. Let me put an agent here. Here's another one. Let's put an agent here, and so on. And then we want to reuse it. But when you go to horizontal reuse or vertical reuse, this is the actual thing that's going to change. That surrounding environment, that's the thing that's going to change. You know, sometimes, oh, now it's synthesizable, so I cannot do this set of sequences that I've just described. Sometimes the interface is totally not there because a piece of the DUT is going to drive that traffic. We cannot reuse this approach, mindset. So if you take one thing out of this presentation is that mindset, we're not thinking outside in. We're defining the scenarios from internal point of view. It's not the spec level, but here's the abstract scenario space of this device. That is going to remain the same in whatever level of abstraction you're going to use it, even to the level that the architect wrote it. That's going to stay the same. Here's the functionality of device that I want to exercise. So that's how we do it, inside out. Tell me what activities this device want to do. It's very custom. No one is going to tell you, like, here's the Ethernet protocol, here's the USB protocol, buy a package to it. No, it's your device. You model your own specific ideas that your architect put together, and that's what you want to exercise on multiple levels of abstractions, including emulation, right? So we're basically defining the actions, the high-level actions in here, and what it is that we're going to do on the interface. This is a secondary thing. I'm going to use a UVM VIP. Great. Here it is. I'm going to use a synthesizable VIP. Here it is. I'm going to do a test card. Here it is. It might be that they work on a totally different level of abstraction. Oh, I don't have the refined control that I have in my UVM VIP. But as long as the side effect is the memory buffer that I need, I'm good. Things are going to work together. If you instantiate a different test card model with its own actions that provide the memory buffer that I need, great. This scenario will still work. This is the type of reuse that we're working on. This is the portability aspect of things. Both on the interface level of what is it that we're going to drive, what language, synthesizable or not, but also on the level of strategy. So this is about the reuse of IP models. You can see the actions in here. They're very abstract. I don't even say which memory am I connected it, who the providers to this, all of these things, totally isolated, right? That's what actions are, inputs and outputs. To the outside world, the integrator will decide what to connect them into. Here's more examples, maybe that once you start using this thing, you'll have to get familiar with. So our CPU, you see we have an abstract software operation here which locks the core because this is the CPU core. And we have check data, which is reading a source buffer, and probably doing some checking to it. Write data, which is outputting some memory buffer. And we have copy data that is reading and writing. So we have source and destination, and of course, this size is the same. So this is our CPU, and we can instantiate, in our case, 4 of them. So we have 4 cores. And we consume, you see, we use inheritance in here to derive from the software operation. So each one of these actions is going to lock the core for the length and duration of this activity. As long as I'm copying using the CPU cannot do anything else. Okay? And of course, for the resources that Tom mentioned, you can define attributes to it. So there could be a core tag and a cluster tag, and this is how I describe the hierarchy of my compute subsystem. Cluster A means that the core tag is core A0 and A1, and B means B0 and B1. I have the hierarchy of my compute subsystem in here, which, by the way, I may care about or not if I'm going UVM using one master, and that's still fine. Okay, so this is the instantiation, and I can instantiate a different cluster. We mentioned inheritance. Just want to show that there's also the ability to override type, sort of a built-in factory. I'm not going to go into that into more details. You can do the override by type or by instance. Now let's talk about the activity. So we put the rules. Here are the subsystem, and here's the activity that each one of them provide with the resource requirements or not. So now I want to write a scenario, and So Dev mentioned here, we want the scenario to be simple, abstract, and so on. So here it is, in a very abstract level, our activity. I can do, here's the CPU, crypto, I can do write, encrypt, copy, decrypt, and check. So here's the activity. Write, then encrypt, then copy, decrypt, and check. I want them one after the other. The nice thing here is that the tool can check this activity in here. This is not sequences of UVM. You just throw them out there. You program the same device to do two different things at the same time. Who knows what's going to happen, right? Here where the rules, the scenario rules, are going to be used. So if two things cannot happen one after the other, they must be at the same time. The tool will tell you, hey, you cannot do that because these two things must happen at the same time. Or it will insert, if possible, a way, we'll find a way that maybe you didn't think of to make this, maybe coming from the verification plan item make sense. Now, we have the input and output. I could, if I want, just say, hey, here's the set of activities that I want, and I don't care about the information flowing from specific action to the other. But I could be very specific all the way, and this is what I did here. So I'm binding. So from write out, I'm going to the encryption source, and from encryption to copy, sort of. So I'm doing a chain here. I didn't have to. I could do a loop of DMA memory, right, which is not chained. It's going to be, I'm copying from one place to another. More chaos, more fun. If I want to, it's up to me to decide. A simple manner of constraint. So here it is. We're going to start. We have the flow here, and here's the data buffer that we carefully bound because that's exactly what we wanted to achieve. Now what happens if I do the schedule? I can do one after the other. I can do parallel, or I can do schedule. We're taking the randomization here to the next level. Oh, if they could be like this, that's fine. Like this is fine, and like that is fine. It's all about what's legal or not, because I don't want to get illegal tests. That's the worst thing. So here's the schedule. I have two chains, the same chains happening at the same time. So the order in here is going to be exactly the same because it's carefully specified. But if I have two cryptos in here and only one crypto engine, the semantic here allows tools to basically say, okay, there is a conflict here, but I can put a sync point here. Basically make sure that this crypto activity is done before I start another activity. This is the kind of thing that users do with their own fingers when they write tests. Oh, I tried to do these two things at the same time. I don't know what's happened right now. But if you do it like that, then it will create a sync point. In the UVM terms, it's basically to create your virtual sequence, right? Oh, wait with this interface because you're not done. Only now activate this interface. So I'm going to find some random scheduling for these things. You have coverage to do whatever you want, what happened at the same time, which is going to be covered later on. But that is the kind of things we're achieving here, and they are much more critical for system level. So basically one operation is going to take place before the other, and so on. So the resource conflict will be resolved. If there's no solution, legal solution, you'll get a contradiction error because this is illegal. From whatever rules you provided, this is illegal. Here's coherency. Coherency scenario, right? You cannot do that in subsystem level and system level. That is a big thing. Cache coherency and I/O coherency, how do I mix them together? It's my own I/O devices, even if I bought my compute subsystem. So how do I do that? So CPU core writes data to a cacheable region. A different core and a DMA read that same memory region. Okay, I want to get this race on the cache line here. How do I do that? So here's my operations, but let's look at the activity. I'm going to do write for a cacheable area. And then in parallel, I will do copy and check after it, and transfer and check after it. But these are happening in parallel. See, with the core, I selected a different core than the one that did the write. It could have stayed with the same core, but I wanted it to be a different core. And I have my transfer here, which is ongoing. Okay, now I want to say, oh, but they're actually writing to the same memory buffer that was sent before. Okay, so just bind it like that. So take the result of the write, and this is what the copy and the DMA transfer are going to refer to. So here's the write. It's going to write a data buffer. I'm going to spawn in parallel memory to memory transfer and copy data, but they're going to take the memory buffer coming from the same write. So now I provided the same scenario. And how do I make sure that the check will actually check the memory buffer of the copy? This is where the binds here are helpful for. Okay, so I define a coherency, and now I can run all of that in a loop. Runtime loop, gentime loop, whatever it is. Okay, tons of scenario. Okay, so this is how I'm leveraging those pieces to create the scenario space. Okay, and this will work even if I use real cores, RTL calls, or just masters, any kind of other masters. Now, let's talk about some of the non-functional aspects that needs to be verified. For example, low power. So we have that team that created all these functional use cases of copying and moving data all over. And now there is the low power team. So here's the spec of it first. So there is two domains, A and B, and each power can be in mode S0, which is the active mode, and S1 or S2, which is two different sleep modes. And subsystem operations depend on respective domain active state. So see, our graphic subsystem belongs to domain B. So it must be active if I'm doing any kind of decode on the graphic subsystem. And the UART and crypto are part of domain A. This is the spec. Now, what I want to do is, of course, use all the scenarios that were there before. But now there's new low power concerns that I need to take into account. I want to, well, maybe before you just power up the entire system and you do your functional test. But now there's a new concerns. I need to take that into account, and I do want to run the entire regression that was created before. How do I achieve that? So let's talk a little bit about state variable and how beautifully PSS support those. I can define a state variable. It's basically just a struct in here. So I have an object here that has domain A and domain B, and we have enum here, S0, S1, and S2. And I can say initially, this state variable is initialized with domain A is in S0 and domain B is in S0. Okay? I define now a state variable. And now I have a new action, which is change power state. I'm reading the state variable and I'm updating the next. So previous and next. That's the action I can do. And of course, if you think about implementation, I may have a C call here that makes this transition software in C, or I may do it in UVM, but I basically define my state variable. This is what PSS allows me to do. And I can instantiate it. So here I'm instantiating on the top, and I'm binding whoever going to talk to low power, take this state variable. Okay, whenever you have input and output. And look at what we're doing here. I can extend the decode action, and I can say, by the way, you have another consideration here. You have another input, which is the state variable. Take that into account, because you need to make sure if you're going to be activated or scheduled to run, the domain B must be in active state, S0. Here, I just introduced another low power consideration, which was not there before. This is why we have the extend. And the encrypt of the crypto engine, you belong to domain A, and domain A must be in S0 active state when you are going to operate. So you can schedule whatever scenarios you want. You as a user can change the low power modes to do whatever activity you want, and it all makes sense that there's going to be a legal scenario eventually executed. So here I just put all the dependencies on top, and now I can do things like do change power state that domain A is not active, and then do encrypt. Okay? I ask for something in here. Here's the change power, and then do encrypt. But as we know, this crypto expects domain A to be on. What will happen? The tool can decide, okay, so I need to introduce another transition to make this legal. It's up to you to say, oh, don't do anything for me and let me know if it's an error, if I have something illegal. Or you can say, oh, go ahead, do all the mixes you can. Enable what was written in the verification plan because this is what was written. So the way we define the semantic is that if someone wants to support this standard, the tool must be able to find out how to make this partial scenario a complete legal one. Okay, so this is what you see in here. So we changed the power state, and B was randomized to be S2. Now there's going to be another power change introduced to power up domain B so we can do our encrypt. All the scenarios, even if I didn't touch the power, now I can introduce power to them. Here's another type of activity. I'm going to define an action which is random activity, which is just going to be a selection of copy, encrypt, and decode. Random activity. And now let's define another scenario, which is repeatedly do some change for power state and then randomize activity. I can do repeat 2, I can do repeat more. But this is what will take place. So we start, the power state is S0. We randomize some change. Maybe domain A become S2 right now. When you come to the select, encrypt cannot be executed. So the tool will choose one of these two, which is legal according to what was generated. And I'll randomize another power change, and I'll maybe decode, because domain B is one. Decode is illegal. Now I'm saying it in a procedural way. This is not procedural code in any way, and not procedural solving in any way, right? Because you can get yourself very, very quickly into, a power down all the cores, and now the system is locked. I have scenarios like that when, sometimes it's real hardware. Someone needs to, maybe over the weekend, to go and turn the machine on again because you locked all your CPU cores. This is the kind of complexity we're talking about here. You need to solve all the solution and decide what it is, not in a piecemeal approach. Right? We all know that from, if I just randomize a transition when I'm powering up, powering down cores, I may as well power down all the cores and now nothing will wake up my system without taking into account. So basically we have a constraint solver going on. It is raising the bar on the vendors themselves. A powerful constraint solver here that could take all these into account. We're basically taking randomization to the next level. Randomization that user had to vary in his own code. Now tools will do it.
Hi, I'm Adnan Hamid. I'm from Breker Verification Systems. We are one of the companies that have been working in portable stimulus for a long time. My role in this presentation is to talk about the bottom end of the portable stimulus specification. How do you get from these very nice scenarios to actually implementing the test that will feed your various test benches? The basic concept over here is that we are going to have some PSS model, and we just got through listing about how that can be created. It's going to come through some PSS tool, and then it'll get mapped onto your verification engine, right? There are many different verification engines we use, from UVM to full chip simulation to emulation, FPGA prototyping, post-silicon. We're going to talk about some of these. One point that was made to me is that there are a lot of questions between the actual model and how the test is created. Now, I give you two analogies. One is, in System Verilog, we have constraints, and you say, hey, here's the constraint I want followed. But the algorithm to actually solve that constraint into a set of numbers is not defined, right? So each vendor will provide an implementation of this. So there's this abstraction of this is what the scenario says it must be, and the implementation of the scenario, they're two different things. A second analogy that I often use is it's like logic synthesis, right? We're all used to the idea that we take RTL in and we feed it through some synthesis engine, and out come a set of gates tuned to a particular process. And depending on what process we're going to, the requirements of that process, we might get completely different gates, all from the same input. So that's very much the model being followed over here, right? That an abstract PSS model that can be synthesized down to tests for various platforms. A big piece of having a standard like this is to foster competition, right? So some vendors will look at this and say, hey, maybe the best way to solve this is the infinite minus constrained random solutions, right? Other vendors might say, hey, graph-based problem solving is a more powerful way of solving this, more intuitive to human beings. So we will see different kinds of solutions come out from the same standard. How can a portable stimulus model get mapped onto a particular verification engine? Many different models, right? Let's start with having a UVM test bench. So I have over here my little design. I have my VIPs in UVM in a UVM environment. We might be able to read that model, pass it into a PSS tool that either generates the UVM sequences, pre-generates them, or interactively talks with the various VIPs to generate your tests. If it's running interactively, it gives you runtime solving. Depending on how you do the interface between the tool and the UVM environment, if you're doing it with templated code, it might not be portable. If you're doing it some other ways, it might be portable, and I'm going to talk to you about these different mechanisms. Another model is for software-driven verification. Right? This is where we have a design that has one or more CPUs in it, and what we need is a C-test to be generated for that design, and the tool will generate that C-test for us, and somehow that C-test must also interact with the VIPs, the so-called trick boxing problem that always comes up in system verification. So this says that we're going to do generation time solving. In other words, at runtime, we're not doing any solving because maybe this is a full chip simulation. We've already generated the test, and one implication of that might be that we have limited reactivity. Right? We might be able to react to certain things like waiting for an interrupt, waiting for a certain condition to be true, even do some if-then-else clauses, but it might be difficult to do a completely different scenario depending on some reactive result from the design. And then another model might be that we put the entire PSS tool on a target. Some of these are very easy to imagine, right? We could have this tool running on a Linux box and feeding various cards to do various test cases. If some vendor can figure out how to do all of this solving on bare metal, then maybe the tool can be put on there. This would require a pretty fast system, right? So I'm not trying to say that we will or will not do this. The point is over here is that the portable stimulus standard is abstract enough that it lets vendors translate these to different solutions, and different people can go after different aspects of this market. So let's get down to the nitty-gritty of the actual implementation of these test cases, okay? So these are based on this notion of exec blocks. Exec blocks are effectively functions or function calls or blocks of code that get executed at various time, okay? So you can have an exec block anywhere in your model, but they mean they're different types of exec blocks, and they mean they relate to different phases of the test, if you will. So the very first type of exec block is a header exec block. Anything that you put in there, it is to generate code that will go into the very top of your test. And the typical use case is having an include or something like that. Next thing is declarations. All right, so these might be a section that you use to define functions that need to be generated into your test case that maybe take advantage of headers you've loaded, right? So far we really haven't done anything very profound. Then we have a run start exec block. This is something that will execute once before the test actually starts. So the first two were declarative kind of things, right? They were just bringing things into the test case. This one will actually execute something once when the test begins to run. A fundamental concept of tests generated from portable stimulus is that they're concurrent, right? They're threaded. Whether they're threaded in UVM, they're threaded in C, how the thread is doing, we don't have to discuss, right? Maybe they are Linux threads for all I care, but they are concurrent tests. So there is some kind of threading system presumed. This is supposed to be a representative output of a tool, right? Nobody's saying that this has to be the output. But something that will go off and fork a bunch of threads, and those threads will run. Okay? Within a thread, we have a sequence of activities that we're going to run. For each activity, and this is now hopefully hooking up to what you've seen so far before, right? I'm talking about the lowest level actions that map to implementation of the test. So for each of those, we have a pre-solve exec body. We're actually going to solve the action. And then we have a post-solve action body. And then finally, we have a body function. So these are all different points at which you can do actions. And perhaps in that body, we actually put down some function call that we need to do within the thread. And that repeats for every action that will happen in a thread, and note that there are multiple such actions in a thread, right? That's what I'm trying to show over here. So what you're seeing over here is a system where we start up, we include some stuff, we declare some functions, we do our initial run start, and then we do a bunch of actions, each of which can have the body exec blocks. And then finally, at the end of the test, once everything is finished, we'll call our run end exec block. Okay? So it's a pretty straightforward, simple view of thinking about what's going to happen in your test case. It's what do we have to include at the top, what things do we have to declare, What do we do when the test starts? All these threads fork off, the various actions run, and then when they all finish, we have something to do at the very end to clean up if we need to. So the threads, depending on your needs and which tool is running, tools options, they might be multiple cores, they might be soft threads running on one core, they might be multiple hardware threads, whatever's going on, right? Finally, there's one more piece, which is the file exec block. This is for doing things like creating makefiles or other scripts that you want generated as part of this test. So it's an arbitrary file in which we could put in whatever we need to make the test run. This stuff tends to be part of what happens when you're randomizing a test. You have some configs that have to be perhaps loaded when the simulation starts, and so on. And I've shown you over here an example in C, but there's nothing specific about C over here, right? This could be in System Verilog, it could be in any other language that your test bench wants as an input test. Okay, I'm going to talk to you about 3 different ways that an exec body can be implemented, okay? One is based on textual substitution, right? So we can define text to generate into the output test. The second is based on calling imported functions. And the third is based on calling the hardware-software interface. That's something we'll talk about after I'm done. So let's start with defining the implementation using these exec body strings, right? So this is a text substitution mechanism. So the idea is I have over here exec body with some string, and things in these double braces that we call the mustache construct will be replaced by the value of that construct within that action, right? So it's a substitution, and we can feed that into whatever test is being generated, right? So it allows you to create arbitrary text in your output test. So this could be SV code, UVM code, C code, as we'll see in a second, right? So how would the test look if we generated from that? This code was generated from the exec body text substitution, right? So we had the init UART RX call with some values filled in and the gen UART traffic call with some values filled in. And that's what showed up here and here across 2 iterations of the test. And that can be coupled with some implementation of those operations that you have already done. The implementation of this UART init RX is right over here. He's configuring the UART register and updating it. The setup for this gen UART traffic is driving some sequence on the VIP. So very simple way of doing text substitution to create the test that you want. So what happens now when this thing runs? This is the test that got generated. When we call init UART RX, it will call this task. That task in turn will call the register layer in UVM, which in turn will call perhaps the AXI VIP and program the UART. Similarly, when we fork off this sequence down here, it will go run on the UART VIP and send some traffic into the UART. Let's do the same thing, but now we want to generate a C test. So instead, our exec body might say the C variants of these functions also filling the values, right? We're still on this template substitution model. So now we can go generate our main function with whatever threads, whatever we need to do. But now we have C calls in here, and those C calls have been previously implemented by you, and those are what get invoked. So over here I have a C call that is writing a register in the UART, and over here I have a C call that is talking to some kind of a trick box mechanism that can go communicate with the VIP. How about if we're running this in a completely different platform, right? So the important thing over here is my first example, we ran on a UVM transactional test bench. In the second example, we ran on a software-driven environment with a CPU in the system. And now we're running in a completely third system. Perhaps we have our design sitting on a PCI Express card that plugs into some kind of host, and our tool is running on this Linux host, right? In this case, we might generate the same test, but when we call this init UART RX function, it'll turn into a PCIe write function that'll go to the UART. And when we want to do a VIP transaction, we'll come through the UART interface of the host to feed the card itself, right? So we feed both ends of the card. So the point we're trying to make is the PSS model is completely abstracted from the platform, and the tools can map them to various different platforms, right? And the first way of mapping this is by generating different text substitutions into the output test. Second mechanism, using import functions. So this mechanism says that we will write functions in an external language, typically C, C++, and we can call those functions from within the portable stimulus model. Right? So over here, what we're saying is we're importing this init UART-RX function, and we're importing this gen UART traffic function. And the idea is that you have already implemented those functions offline, and we're pulling those functions into the model. And we will invoke them at the right point in the test case. So now in our exec body, it looks much more like a function. And instead of substituting text, we're actually calling the imported functions with the appropriate arguments. So our resulting test might look very similar, right? We might end up in UVM. Your call might generate the call to the appropriate UVM task. And again, we are driving the UVM VIP for the UART to program the UART as well as to generate UART traffic. So that's in our UVM simulation with no CPU in line. We could do a software-generated test in a very similar way. That test is now a C test generated from the portable stimulus tool, and takes advantage of functions you have previously written that implement those functions in a different way, right? In the UVM environment, when we wrote a register, we had to go to the AXI VIP. In the C model, when we want to write the register, we got to write the correct address from the CPU, right? So different ways of mapping. So this again says that you re-implemented those functions. And the same scheme would work in your PCIe-based post-silicon environment, right? We don't have to import any different functions. The functions can generate calls to your pre-created functions. And the reason it worked is we used one implementation of init UART-RX in the software-driven flow and a different implementation written by you in the post-silicon flow, right? So you are replacing the calls underneath to achieve what you want to achieve. And then finally, there's the so-called hardware-software interface abstraction, right? So the hardware-software interface abstraction says that we can write a set of objects, we can create a set of objects as part of the standard that abstracts away you having to manage how these things get driven to the design. So for example, we might make a call to the Accellera that says, please go configure my registers, and that might call some register package to go set up and write those registers. We can make it look a lot like UVM, but it's been moved up to the portable stimulus layer so that the tools can manage what happens with them. Similarly, we will have something to drive I/O transactions, right, so that we can feed VIPs. And the idea over here now is instead of putting the mapping work on you to translate either what textual substitution happens or implement the underlying imported functions, the tools become responsible for managing these things. So what would that mean? Here's a portable stimulus model now in C. From the body, we can directly call the HSI function. And that function is responsible for managing the mapping to go talk to your AXI VIP in UVM, right? However the tool vendor chooses to do it, right? So no longer your problem. Similarly, when you want to drive the data on the UART, it's up to the vendor to map how that actually happens and how it goes to your UART transactor. One solution could be that they pre-generate a sequence for the test bench, another one they can run interactively, and so on. If you're coming to a software-driven flow where there's a C test in the mix, then all those register writes need to be turned into C code to do those register writes. It means that the vendor's tool is managing all your register maps and so on. And again, the transaction writes have to be mapped to the VIP. And again, it's up to the vendor to manage how that happens, right? Taking work away from what you have to do manually and putting it back on the tools. And then finally, if you're going to a post-silicon flow, where my model over here is that we have a PCI Express card, then these registered writes become PCI Express writes like we saw before, and the transaction writes perhaps come through the UART and drive whatever I/O transaction needs to be driven into that card, the trick boxing problem.
My name is Srivatsa Vasudevan. I work for Synopsys, and I'm going to be walking you over coverage in portable stimulus today. Earlier, you've heard from Sharon on how powerful the tool is. You've also heard from Tom, and then you've heard from Adnan on how different use models can be deployed. And throughout all their presentations, they've gone ahead and talked about how randomization is such a powerful feature. Well, the moment you introduce randomization, coverage goes hand in hand. And in order for you to measure exactly what you've gotten at the end of the test. So I'm going to walk you through some of the concepts in portable stimulus as far as coverage goes. And you will see that it's a fairly intuitive step up into an abstraction layer where you can ask some of the more important questions and get answers that you probably had a tough time doing earlier. So we're going to walk through a few of these things today. I'm going to go over what coverage is and coverage is not in portable stimulus. I'm going to define what scenario coverage in this particular instance means. I'll talk a little bit about coverage monitoring, and then we'll go over a couple of usage examples. So let's talk a little bit about portable stimulus coverage. First question is, we are all familiar with UVM. We've had a number of discussions on UVM. You guys have been verifying for a very long time. Is it code coverage? The answer is certainly not, because in some situations like emulation or so, it may be possible to get code coverage. Is it functional coverage? Could be cover groups, but not at the low level, right? Some implementations may not have some aspects of it, so it can't be just called functional coverage. Is it test coverage? Now you've gone up one level, saying, hey, look, it's my whole test. Okay, but can't we do better? So basically here, you might want to define coverage as saying, hey, look, if my test passed, this scenario got covered. But that's a very, very abstract view. And we actually have to go down a little bit into the details, as we can see here. So let's now talk a little bit about the opportunity. Along with different types of coverage, okay, you have the ability to ask a number of very, very important questions. Was I able to connect all my blocks correctly? Was I able to address all my blocks? Did I walk through all the power state sequences that I wanted to? And did I use all my resources if I was using a DMA? So you've earlier heard that we are actually able to have a declarative model. So it basically means that since we have formalization of system level scenarios, you're able to formally describe these scenarios, okay? You're actually able to describe these scenarios in a formal sense. So now we have introduced randomness, so we need coverage to confirm usefulness. One of the challenges with portability is that collecting coverages in non-simulation environments, there may be a lack of visibility in certain hardware platforms. If you're using in-circuit emulation or something, or running on an emulator, or you've got a black box with something, traditional coverage can be quite difficult to collect, okay? So we have to raise the level of abstraction a little bit. So I'm going to go back to this slide where we talked about coverage. Earlier we saw a number of various use cases. You could have a TLM system C model, you could have a simulation model, you could have customer boards, you could have a virtual emulator in silicon, or a tester, okay? And various PSS models, in this case, could have come to you from various sources. So you could technically look upon this also as an aggregation, okay? So the coverage itself is a little bit more abstract, and therefore, what you'll see now is you'll have a different set of types of coverage in portable stimulus. Action coverage, so where all the actions that you defined executed, or did you actually execute a subset of these actions? So scenario coverage, somebody here was asking about, is this control flow only or data path only? Scenario coverage will actually tell you what legal sequences of actions were actually executed. Then you have data path coverage. I went from source A to source B. Did I cover all my sources and sinks? Remember, the tool is actually generating a whole lot of scenarios. At the end of the day, one particular run from one particular test may only cover one portion of the graph, okay? But when you look at the coverage as a whole, you can remain assured that all possible sources and sinks were actually covered. And then values. We just talked about sources and sinks so far. So think about value coverage also, okay? This is one of the things so that you can actually measure, hey, look, I wanted to make sure that there was a size 20 that went between the UART and the DMA in my example. Resource coverage. You have a number of resources in the system, and therefore you want to make sure that any resources that you added into the pool were actually used. That way hey, look, I've been able to test my design completely. So you might want to cross any one with any of the others, okay? This is a common thing that we see. Right now we have scenarios, because the tool has actually gone through them. The scenarios are all legal behavior, okay? The tool makes a choice between the 2 points. You've described things at a very, very abstract level, and then you've described resources and things and said, tool, please generate these things for me. As you've done that, now the tool knows, okay, fine, this is my input, this is my output, and I can basically enumerate all the choices between them, okay? The tool is able to do that. The tool is able to figure this out. Since the tool is able to figure this out, it can also target the coverage. But here's where the interest comes. With great power comes great responsibility. You can easily write a coverage model that has more atoms than there are in the universe, okay? You have to think through and decide what is important to you. And your tools will probably give you a feedback saying, hey, look, you're trying to do something way too big, it's going to run forever, you're not going to get your quality of results. But basically that flexibility is up to you. So now let's go through how we monitor coverage. Coverage is of 2 kinds, okay? Stimulus monitoring, what is it that you're actually feeding in? So as long as the test passes, you can deem the coverage data as valid. You can think of this just like a back to school checklist. Okay, I'm still being very abstract. I'll get into a little bit of the details and you'll find it's fairly simple. But it's just like a back to school checklist, of all the things that you probably want to put into your bag before you actually go to school. The second is called runtime monitoring. This is, as you go through the motion of going through a class, it could be C or C++ code running on a target CPU, could be a trick box that's occasionally feeding data to an outside coverage collector. It could be classic coverage in the UVM case. Or you could have a spy port that's actually sitting there collecting data off of the board. And we call this pretty much like kind of grade that you get. So don't think that B- has anything to do with a portable stimulus. That was the easiest icon I could find. So let's go through a couple of very simple usage examples. And what you're going to see is, let's talk about a simple thing. You want to cover whether all your resources got utilized. A good example would be, hey, look, did everything cover my resource with type equal to SRAM? That's a simple question you may want to ask yourself at the end of it all, to say, hey, look, did everything come out of the SRAM at one point? And then we're going to walk through a couple of very simple UART and DMA examples, and you'll see it looks very, very intuitive. Okay, let's go through the UART example. This is the same slide that you saw last time. Pretty much you got a UART, you got a DMA and a memory. If you remember, here comes the quiz that we were talking about. Okay, the UART is actually getting data out of the memory and then feeding itself out. So you've got these actions that basically allow you to transfer data. The only thing significant here is that we've added a cover spec, saying, hey, look, here's the cover. I want you to keep track of these bins. This kind of construct is very, very similar to the system umbrella construct. Okay, but it's at an abstract level. Allows you to cover the fact that, there was a size transmission between 1 and 20. Let's talk about a second example. Here now we're talking about covering data that's actually going through a DMA buffer. And here you've got an input buffer and an output buffer, a source size equal to the destination size. And what you've done is basically covered the source location, the destination location, and then pretty much created a cover point across the two. And therefore this is an abstract model. Okay, this is pretty abstract. But fundamentally you can cover this going this way or this going some other way. So now extending the same example, one thing you can do is you can realize that it's not constrained to those 2 or 3 physical things you saw in your system. Okay, it's just not constrained to that. You can raise the level of abstraction a little bit higher. And then you could basically have actions that are moving data from your USB to your HDMI and then wondering, did I cover all sizes of scenarios? And therefore, you can think of this abstract thing having a cover spec for itself. And this might help you to actually answer some questions about whether, hey, look, did I cover all the paths in my system?
Hello, I'm Karthik Gururaj and I'm a principal architect at Vive Labs. I will be covering the next section of this webinar on hardware-software interface library along with my colleague Sandeep Pendarkar. So the story so far is that we have seen how portability of test cases can be achieved to different verification environments and to different verification platforms, how one can go about capturing complex use cases, and also how to measure coverage. But there is one important missing piece we haven't looked at yet. Let us look at this picture again. If the tests generated from a single abstract portable stimulus module have to seamlessly run on different verification environments, then the generated code must necessarily have all the required intelligence for interacting with the hardware, be it programming registers or descriptors or reacting to interrupts. All this information must be present in the generated code, and hence it has to be codified and captured as part of the abstract portable stimulus model as well. So, what is the information that requires to be captured? The HSI specification of a device serves as an abstraction for complete device management, be it performing device initialization, configuration, or operations such as transmit or receive. The proposed HSI standard has constructs to effectively capture such a device specification and will effectively serve as the programmer's view of the device. How does HSI relate to what we have already seen so far? The scenarios and the use cases that capture the test intent ultimately rely on leaf level actions. And these leaf level actions capture all the interactions with the underlying hardware device. The definition of these leaf level actions will be done using the constructs provided in the portable HSI specification. And the definition will include all sequences required for interacting with the hardware, like sequences for initializing the hardware, configuration of the hardware, data transfers, etc. Now, as you have probably guessed by now, the HSI specification will be specific to a certain device or IP. However, it is recommended that different devices that all belong to a same category, all these different devices, they use a uniform interface, which would then make it possible for scenarios to remain portable across devices. So we'll just look into this in a moment. Let's put these concepts together and review what HSI enables for the end user. The DUT mentioned in the box at the bottom is a DMA controller, and the different verticals represent different verification environments. The RTL simulation on the left to an FPGA environment with an embedded core on the right. What you already know is how the stimulus, whether the test cases in System Verilog or C test cases in other cases, you know how the stimulus can be generated from a single portable stimulus model. Similarly, the implementation of the leaf level actions, again, be it in System Verilog for simulation or C for FPGA use cases, will be generated from a single HSI specification of the device. This ensures the scenarios that are captured in the stimulus model stays portable across different verification environments. As another application of HSI, let's revisit the example used earlier. A subsystem of a SOC that has a UART and a DMA controller from some vendor. The device driver, by the way, we use that in a generic sense. We mean the component that interacts with the hardware irrespective of the language of implementation or the verification environment. So the device driver for these peripherals will be derived from the corresponding HSI description. And the test cases for the subsystem will be generated from the scenario model. Now let's imagine that the subsystem changes and we now have a UART and a DMA controller from a different vendor. The drivers are generated as before from HSI specifications of these newer peripherals. However, because of the abstractions in place, the test cases can be generated from the same scenario model. This is possible because HSI can abstract the scenario model from device specific details. So we can have a single specification for the test scenarios, which can then be reused across these two subsystems. And this can be quite a powerful methodology. A typical SoC has a significant percentage of off-the-shelf standard IPs. With standard constructs for representation of HSI, it is possible for the IP provider to provide the HSI specification along with the module. So the IP provider does not need to bother with the specifics of the verification environment for their customers, who can then take the HSI specification and generate the code for their desired verification environment, be it simulation or emulation or OS based test environment. So if you contrast this with the situation today, where the customers get a data sheet and hopefully a reference driver, typically for a specific version of Linux kernel, a reference driver that can be very hard to port, so you begin to see the advantage of this approach. So using HSI as an integral part of your portable test stimulus modeling methodology will really ensure that the test intent stays portable even if you switch devices in your SoC. Let's again recap the important elements of the hardware-software interface specification. So we're not going to go into details of each of these, but let's just take a look at it quickly. For a start, we do need to capture all the programmable registers of the device. Typically, this would be derived from an IP exact or a system RDL description of the device. Virtual registers, which refer to data structures in memory whose layout is defined by the device specification and are typically used by devices that can perform scatter-gather DMA. We need to also capture the virtual register specification as part of the HSI. And for such DMA capable devices, we need to also capture the descriptor layout and management. Basically, whether the descriptors are laid out as an array or linked list or some other fashion. So that would be needed. Synchronization of ownership of DMA buffers in memory between hardware and software is another aspect that would also be captured. A device may issue multiple interrupt signals, and each of those can be triggered again by multiple interrupt conditions. So this hierarchy of interrupt events, along with the information on how to enable, disable, clear and query status for each interrupt condition, will also need to be captured. And finally, we specify the sequence of operations for initialization of the device, configuration and other operations that make sense for that specific device, could be transmit or receive. So all these sequences are also captured. And the definition of these sequences will make use of other aspects of HSI. For instance, the definition of sequences may read or write to registers or virtual registers, or may poll for interrupts, for example. So while we are recommending a uniform abstraction for different devices in the same category, not all devices are created equal. Taking an Ethernet MAC as an example, one implementation could very well be very simplistic, requiring the software to implement many of the higher level operation. And there could be another implementation that offers hardware acceleration features to reduce the load on the software. For example, the hardware MAC might be capable of parsing an incoming packet. For specific fields, it might be capable of calculating checksum, timestamping packets, for example. So we can capture the capabilities of a specific device in a sequence for establishing the capabilities. So this is important to ensure the portability of the test scenarios that then will utilize the HSI sequences. Let us now revisit the DMA allocation example that was covered in an earlier section of this webinar. Note again that this example is in pseudocode. You can see that there are three actions defined for this duty: memory to memory transfer, memory to queue, and queue to memory. And as you can also see, the signature of these actions in terms of what the inputs and outputs are, they are also defined. Using the portable constructs in HSI, the definition of these actions can also be captured. In this case, in terms of register read writes and polling for one single interrupt. For example, in this case, the source, destination and the size registers for a DMA channel are being programmed and the control registers are being configured. Finally, the DMA enable is being set, which will kick off the DMA transfer. It would really trigger the hardware, finally resulting in a transfer complete interrupt being triggered. So the last statement in this sequence is essentially to wait for that interrupt. The definition for other two actions are quite similar. So obviously the registers that are being used in these definitions must be declared elsewhere. So this example just shows a pseudocode again on how the registers can be declared. And again, typically these will be derived from an existing IPExact or system RDL specification. Similarly, the interrupts used also need to be captured. So just to understand what HSI specification really means for a tool, let's take one example here, the last statement, which is the wait for an interrupt. And let's think through what it really means for the code generated from HSI specification. In a simulation environment, perhaps using system Verilog, the wait can translate to an event getting triggered when a port value changes from 0 to 1. However, in a full SOC environment, waiting for an interrupt from a device can become a lot more complicated. The interrupt line from the device could be connected to an interrupt controller on the SOC, which then needs to be programmed to forward the interrupt to the processor. When the interrupt arrives, when the processor gets interrupted by the interrupt controller, a first level interrupt handler must then run, which would then determine the source of the interrupt as being the device. So a tool that understands these characteristics for the target environment can translate a single HSI specification. This specific line in the HSI specification, it can translate it to either of these two environments, be it observing a simple value change for a port, or be it waiting for the ISR of the device to execute. Sandeep will now get into more details with the DMA controller as an example, and I will come back to summarize at the end of the section.
This is how the HSI specification would look like in C++. So this is how you define a register. Pretty much straightforward over here. You could group the registers as well. So you could have a grouping according to DMA channels. So you could have a group that captures the source and destination registers. And you might have multiple DMA channels. So you group all of that together in a single vector of registers. You declare all your interrupt events in a similar fashion. And then you create a HSI class for this DMAC controller by deriving from PSS HSI, and then these would be the methods over there, the mem to mem, mem to q, q to mem. And of course, there's something called as a build. I'll come to that later. And of course, you need to instantiate your register group as well as the events object. So in the build method, you really attach a bunch of attributes to your events that you have declared earlier. You could have events of different type, right? Like status or error or read and write. So you could specify that. How do you enable interrupt? How do you disable it? How do you poll for a status at any given point of time? And of course, again, the same mem to mem transfer code, but this time in PSS C++ syntax.
So to summarize, specifying the device's programmer's view using portable constructs in HSI really enables us to generate the device driver for different environments. It could be for block level test environment, either in system C or system Verilog, or it could be a bare metal environment that uses plain C code with no OS, no operating system, typically used for performing bring up tests, or it could be for testing over a complete OS for the final product. That brings us to the end of this section. Thanks for listening. The next presenter, Faris Khundakjie from Intel, who is the chair of the Accellera's Portable Stimulus Work Group, will walk us through few concluding remarks.
So what we're trying to do here at the heart of it is separate the what from the how. Okay, it's not to get you to think at a very specific abstraction level, but to separate the what from the how, specifically the how of when it realizes on the target platform, whether it's simulation, emulation, post-silicon, virtual platform. Keep that in mind. So you might walk away with the perception, I have 3 different ways of doing exec block. These are parts of mapping to the how, right? They're possibilities. They're not your input. They're not your intent for portable stimulus, okay? Now, we walked through specific deployment use cases that are real pains to us, right? So we think that portable stimulus will actually solve these problems. Generating a driver with different links, or generating your OVM, UVM sequences, or talking to them, or generating C code instead of that, or syncing these. These are real problems we have today. So please go back, look at your environment, look at the inefficiencies you have. I'm not going to go through the portability across platforms, users, configurations. I think we've given a lot, especially on Adnan's section, a lot of deployment models. This is a serious effort. We have 18 companies here. We're looking in the second half of the year to come up with an early adopter release. We've been at this since the beginning of 2015. The proposed work group that collected requirements was back in mid-2014. Okay? So this is a very serious effort. We do think collectively as users, the members of the work group, as well as vendors, that this is a problem to go after and get the next leap of productivity and quality. I hope you've walked away with key concepts, key constructs you learned today, and walked away with realism of how they map to specific platforms and specific use cases. Now, what we hope you'll do when you go back to your daily jobs, get your voice heard. This can be your company directly represented in the work group. This could be your preferred vendor, or any vendor you choose to talk to and communicate your use cases through. Or could be any of the speakers you've heard from today. Fire up an email, say, how do you solve this problem for me? Okay? We'll take your use case, we'll bring it to the work group. All right? So there are no boundaries here of getting your voice in. Please participate. Now, when you go back, be an agent of change. We all do a good job within our own sphere of influence, within our own UVM, nice, fancy environment. But even if you have already good communication with other platforms, emulation, post-silicon, architects, it's not enough to have it at just documentation level. This is getting it from documentation to actual expression of intent in portable stimulus. Okay? So please go back and talk to more and more folks that pick up your product and take it to the next part of the product lifecycle. Final thoughts here, just thanks to Accellera and DVCon for giving us the real estate. Thanks to the speakers who, again, after 21 updates of slides, put in a lot of hours, a lot of effort into this. And thank you all for listening today.